Hello, I am Paraskevopoulou, and I will present the paper Compositional Optimizations for CertiCoq. This is joint work with John Lee and Andrew Appel. This paper is about a new lightweight technique for compositional compiler correctness. We show how we can use existing compiler correctness techniques to obtain a compositional compiler correctness theorem that allows us to link together programs compiled with different compiler configurations. We apply this technique to compositionally verify the optimizing middle pipeline of the CertiCoq compiler, a compiler from Coq specification language Galena to C. With this compositional theorem, we can obtain a linking theorem for the CertiCoq compiler that allows us to compile programs with different optimizations enabled. This is useful as not all optimizations are beneficial for all programs. We may also want to add new optimizations or reorder existing optimizations and link with code compiled with previous compiler configurations. The key is that the specification of the pipeline remains the same regardless of the particular optimizations that are used, and this is exactly what we need to have a compositional compiler correctness theorem. In the rest of the talk, I will describe how we can achieve such a compositional compiler correctness theorem using existing compiler correctness techniques. Generally, to verify the correctness of a compiler, we prove that when a whole program is compiled for the compiler, the behavior of the target program refines the behavior of the source. This specification asserts that every behavior of the compiled program, P bar, is a valid behavior of the source program, P. But in this specification, we have assumed that the source program is a closed, standalone program. This is hardly ever the case, as most of the real-world programs consist of components that are compiled separately and linked at the target level. More realistically, we want to be able to compile different program components with different compilers that are verified independently, and be able to say that the behavior of the whole target program, which is obtained by linking the individual target components, refines the behavior of the source program, which is obtained by linking the source components. But this is a hard problem, and there has been a lot of research in the past years to devise techniques for compositional compiler correctness. There are few solutions in the literature that can be applied to higher-order functional languages. Each of them offers different compositionality guarantees and requires a different amount of sophistication. On one end of the spectrum, we have separate ComCert, that uses a very lightweight technique to verify separate compilation. This technique requires only small adjustments to whole program verification, but it is not compositional. Programs can only be compiled with the same compiler, except perhaps some optional same language transformations. As we move across the spectrum, we have Pilsner, which is proof correct using Pils, a novel relation that provides strong compositionality guarantees and support verification of entirely different compilers between the same source and target languages. But Pils is a much more complicated technique than standard compiler correctness techniques. Even further on the spectrum, we have verification using multi-language semantics that can be used to reason about linking of programs compiled from different languages. But this requires setting up a multi-language that embeds the source, target, and intermediate languages. We see that as we move across the spectrum, the proof techniques become more sophisticated and they require much more effort than standard techniques used in whole program compiler correctness. Our solution supports compilation with different compilers between the same source and target languages. We demonstrated by imposing the additional restriction that compilers go through the same sequence of intermediate languages, we can use existing compiler correctness techniques, in particular logical relations, to obtain a compositional compiler correctness theorem. So why is the problem of compositional compiler correctness so hard? Say that we have a multipass compiler comprised of a number of passes that are independently proved to satisfy behavioral refinement. Typically, behavioral refinement is transitive. Therefore, we can derive that the whole compiler satisfies behavioral refinement. However, behavioral refinement is not compatible with linking. So the behavioral refinement specification cannot be extended to separate compilation. So what is linking compatibility? We say that the relation R is compatible with linking if, when a source program relates to a target program, and a second source program relates to another target program, then the whole source program obtained by linking the source programs relates to the whole program obtained by linking the target programs. Therefore, when two compilers are proved to satisfy R, we can compile programs separately through these compilers and obtain that linking such programs in the source and target also satisfy R. But what is this R relation? To specify the compiler, we must pick a relation that implies the top-level behavioral refinement that we are interested in proving. This property is called adequacy. In addition, for the specification to be compositional, this relation must be compatible with linking. Logical relations are a widely used proof technique that are used, among other things, to prove program equivalence and refinement. One of the strengths of logical relations is that they are both adequate and compatible with linking. Sadly, logical relations are not transitive. In particular, say that we have a compiler that goes through languages L1 to Ln+1 with n transformations, and that we have proved each transformation correct using a logical relation between the source and target languages of the transformation. We would like to specify the compiler with a logical relation between the source and target languages of the compiler. But generally, it is not provable that the composition of the individual logical relations that are used in the correctness of each transformation implies the top-level logical relation. So there is no obvious relation that we can use to specify the whole compiler. In this paper, we make the crucial observation that adequacy and compatibility with linking are closed under relation composition. That is, we can use the composition of the individual logical relations to give a compositional specification for the compiler that implies behavioral refinement. Hence, we do not need transitivity to obtain an end-to-end relation. That means that if we have two compilers that satisfy the relation obtained by composing adjacent logical relations, we can obtain the top-level linking theorem that we are interested in. So what is the catch? This relation depends on the intermediate representations that are used in the pipeline. Therefore, it can only be used to specify compilers that have the exact same sequence of intermediate languages. I will now show how this technique can accommodate same-language transformations. In the previous pictures, we implicitly assumed that there are transformations only between the intermediate languages of the compiler. But compilers often have same-language transformations on some intermediate languages. In this picture, for example, we have a series of same-language transformations on language L2 that are verified with the same language logical relation RL2L2. Note that the sequence of such transformations trivially satisfy the transitive closure of RL2L2, RL2L2+. Because same-language logical relations are typically reflexive, the transitive closure of RL2L2 is satisfied by 0 or any other arbitrary number of L2 transformations. Therefore, by interleaving the transitive closure of a same-language logical relation between cross-language logical relations, we can facilitate any number of same-language transformations on its language level. If you look at our paper, you will also learn about a new technique that allows proving divergence preservation of transformations using logical relations. Let me now return to the application of this technique to the verification of the CertiCoq compiler, a compiler from Coq specification language Galena to C. We use this technique to compositionally verify the optimizing middle-end pipeline of CertiCoq, and we prove a linking theorem that supports separate compilation with different optimizations enabled. CertiCoq's pipeline starts from Galena and uses MetaCoq to reify Galena into its abstract syntax tree representation in Galena and to erase proofs and types. Then, after some code simplifications, it translates the code to Lambda ANF, CertiCoq score intermediate representation based on a normal form. It does so either with a direct or a continuation facet style transformation. Then there is a multipass optimizing pipeline that translates the code to lambda ANFC, a subset of the lambda ANF language without nested functions. Lambda ANFC is a low-level representation that does not have closures, and therefore it can be code-generated easily to a first-order low-level language. CertiCoq's backend generates C code that can be then compiled correctly with a ComCert-verified compiler. The lambda ANF pipeline of CertiCoq consists of 7 distinct transformations. Some of them are repeated multiple times across the pipeline. These transformations optimize the code and move to a representation without closures. I will not explain this transformation in detail in this talk, but you can read our paper to find out more about them. Notably, we describe new selective strategies for lambda lifting to achieve modular and efficient closure allocation. All of the lambda ANF transformations, except from closure conversion, are same language transformations that do not change the representation of values. But closure conversions change the representation of closures from closure values to explicitly constructed closures. Therefore, closure conversion behaves like a cross-language transformation. In order to verify the pipeline, we use 2 logical relations. A reflexive same-language logical relation E that is used in all transformations except from closure conversion, and a cross-representation logical relation, ECC, that is used to prove correct closure conversion. The chunks of transformations before and after closure conversion satisfy E+, the transitive closure of E. Therefore, the top-level relation that is satisfied by the whole pipeline is E+, composed with ECC, composed with E+ again. This top-level relation is satisfied by any sequence of lambda ANF transformation that encompasses a closure conversion transformation. We can therefore easily add new same-language optimizations before and after closure conversion and prove them correct with the E relation. Or even add a new closure conversion transformation that, for example, uses different closure environment representations, as the ECC relation makes no assumptions about the closure environment representation. The end-to-end pipeline will still satisfy the same end-to-end relation. At the top level, we obtain a linking theorem for CertiCoq that states that programs can be compiled separately through CertiCoq with any configuration of the optimizing lambda ANF pipeline. So to summarize, we present a novel lightweight technique for compositional compiler correctness that we use to obtain a compositional compiler correctness theorem for the CertiCoq compiler. The key idea is that we introduce is that we do not need transitivity to obtain a top-level compositional relation for a multipass pipeline as long as we are willing to accept the restriction that compilers go through the same sequence of intermediate languages. This technique is compatible with standard logical relations or any other relation that is adequate and compatible with linking. CertiCoq is open source and available at GitHub, where you can download and install it. Thank you for watching this talk.